Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. We left off last week having switched reference frames from the force constant K and the physical length of the quadrupole magnet to phi, which is the angular displacement of the proton in phase space with respect to that central z-axis, and with respect to beta, the amplitude, how far out the proton oscillates in the radial or horizontal direction and in the vertical or axial direction with respect to that central z-axis. That's where we left off at, okay? Using that thin lens approximation to equate those two matrices, this is the value of the force constant we came up with, okay? Okay, so doing that, we arrived at a value for using the thin lens approximation of the force constant K of a quadrupole magnet in the synchrotron at the Fermi National Accelerator Laboratory, Fermilab. We arrived at a value of K is equal to 3.623 times 10 to the minus 3 per square meter, okay? We have gotten initial value for that force constant of a quadrupole magnet, right? That invisible force constant. We can see, kind of, sort of, the force constant in a regular spring, right? We can see that. Remember this. Remember this diagram, right? You have a physical spring with an object attached to it. And we can physically see the force constant, right? How tight that spring is wound or how loose is wound. We can see it. But in the case of a quadrupole magnet, we can't see that force constant, all right? We have to use mathematical equations to get an idea of what that force constant is because we can't see it. And we use the same mathematical equations to get a numerical value for the force constant of this physical spring, right? And there's, remember this is our phase space ellipse, right? Right? Equivalent to my diagram of the phase space ellipse for a quadrupole magnet. Okay, all right. Okay, so back to this. We have derived a numerical value for the force constant K of the quadrupole magnet using the thin lens approximation. Now, you remember how, okay, Let's go back. Remember how we started out with this 4x4 matrix that represents mathematically the effect of a quadrupole magnet on the proton as it circulates around the synchrotron at Fermilab. Remember that? Okay. And as you can see, K is there, the force constant. S is the length along the central z-axis through the middle of the quadrupole, which we put in L, the length, the actual physical length of a quadrupole magnet, okay? All right, that's what we did. And you remember how we took this 4x4 matrix. Again, I know this is review and you just might be so tired of it, but a lot of mathematics, so repetitive is not too bad, right? Here, you have the initial coordinates of the proton in phase space, horizontal position or radial, vertical or radial, and how fast that radial or horizontal position is changing, and how fast that vertical or axial position is changing with respect to the z-axis, trajectory along the z-axis. And when that proton goes through this quadrupole, these are the new coordinates of its radial or axial, radial or horizontal position in phase space, how fast that radial or horizontal position is changing with respect to its distance along the z-axis, the central trajectory through the quadrupole. Its vertical or axial position in phase space, new position, and how fast that position is changing with respect to its position along the z-axis, the axial, the position along the quadrupole. So we have this quadrupole, this 4x4 quadrupole. And if you remember, in this case, this quadrupole represented a horizontal or radially focusing and vertically or actually defocusing quadrupole magnet. The two effects are entwined in the horizontal or radial direction and the vertical or axial direction. They are entwined. And you know I wanted to use that word. And what we did, we separated that 4x4 into two 2x2 matrices. One that radially or horizontally focuses and vertically or axially defocuses, and the other in which it radially or horizontally defocuses and vertically and axially defocuses. That's what we did. We separated those two out into these two matrices right here. We applied the thin lens approximation, okay? All right? So going back to where we left off, we had to insert those drift spaces. We came up with a 2x2 matrix using the thin lens approximation, okay? And we equated that we equated that to this 2x2 matrix where we changed reference frames from the force constant K to the length and the length of the quadrupole magnet to phi, the axial displacement, and beta, the amplitude. Okay, that's what we did. That's what we did. All right? And using that, we got an actual number using the thin lens approximation for the force constant of a quadrupole magnet, okay? And this number, 3.623 times 10 to the minus third meters per minus 2. In English, that would be to say that the force constant K, of a quadrupole magnet in the synchrotron using the thin lens approximation as a starting point, the value is 3.623 newtons of force. Actually, let me rephrase that. 3.623 times 10 to the minus third newtons of force per square meter. So, as the proton is traveling through the quadrupole magnet, okay, it is experiencing a force constant of 3.623 times 10 to the minus 3 newtons per square meter as it passes through that quadrupole magnet, okay? And 3.623 times 10 to the minus 3, let's just move that decimal point over 3 places, right? So what it becomes is that the force constant that the proton is experiencing is 0.003623 per square meter that proton passes through in the quadrupole magnet. You see how we're getting the physicalness of this, right? Right? You got to keep that in mind. Physics and mathematics, yeah, you got your mathematical equations, but you got to keep the physical in it, right? Physical, make it physical. Wasn't that a song or something? I don't know, from the 80s. But you got to do that. You got to keep it physical, okay? So here we have a numerical value that expresses the tightness or the looseness of that quadrupole magnet, okay? All right. And just to let you know, some other variables that we had to come up with is, before we piped all these values into the computer program, we had to come up with the number of oscillations in phase space that a proton will go through as it makes one revolution around the synchrotron, okay? All right? We had to do that in the horizontal or radial direction and in the vertical or axial direction. And what we came up with, using the computer, is that as a proton circulates around the synchrotron one time, in the horizontal direction, in phase space, it's going to do 6.7 revolutions. And in the vertical or axial direction, it's going to do 6.8 revolutions. All right? So let's go back. Here's our phase space ellipse. So what that just said is that as that proton makes one circulation around the synchrotron, one revolution. In phase space, it's gonna, in the horizontal or radial direction, it's gonna go around this ellipse 6.7 times, okay? And in the vertical or axial direction, it's gonna do 6.8 times, okay? That's what they're saying, all right?